Alright, so here's a PC power supply, and it doesn't work, as once I figured that out, I helpfully indicated that with a marker for myself. There's no one else who would like try and use it, but yeah, it's a Corsair 750 watt job. So I don't know how reliable these are in the grand scheme of things, and I don't know how long this one ran. So I'm not actually going to try to fix this. I already have a spare when this when I had to get a power supply. I actually got two so that I'd have a spare and to be able to test it with. Not that I really need mission critical the ability to immediately bring things back online, but more to have a second one to test, to rule out the power supply, basically. So anyway, what happens is it does power up if you connect it to a power supply tester and the voltages appear okay, but you start adding things to it while still maintaining the correct load. Like, I'm not overloading it, but it's shutting down like it's being overloaded, and then it just recycles over and over again and just keeps going. So, yeah, it'd be like... like that. So, anyway... I'm just, if this were something I were trying to fix, I'd guess and say it's bad capacitors or something, and I might see ones that are visibly bad. So I'm probably just gonna, rather than actually try to fix this, I'll probably just take it apart and see what happened, and talk about how a switch mode power supply works and all that jazz. So I'll go ahead and get started on that. Alright, so before I open this, I do know how to recognize a high voltage capacitor and how to discharge it safely without getting shocked. Now, I'll show you how I do it, but if you guys do it a different way, then I'm not going to try to tell you that your way is wrong or anything. So, anyway... But I just do want to warn you that high voltage capacitors may retain a charge even though the device itself has been unplugged, and so that could be a nasty shock, literally and figuratively, to anyone taking it apart. And if you're really unlucky to get it exactly the wrong way, it could kill you. So it's probably better not to take these things apart until you know, like, how to recognize a high voltage capacitor and basically how to discharge them. So otherwise it may not be just the machine that's dead. So these aren't that hard to replace, and they're pretty inexpensive. Besides the danger of like getting shocked by the high voltage caps, which is only really a danger to people who aren't aware of them, but or if you forget about them in the moment. But there's also another risk, that if the supply fails again or something, or if you make a mistake repairing it, that data loss could occur. If it's like connected to your hard drive and it overvolts the circuits on the hard drive, then or the solid state drive or whatever, either of which, in either case, you could end up losing data. And also motherboards and CPUs are generally a lot more expensive than a power supply, so that's one reason I'm not going to try to fix this. Alright, now that I've taken the fan grill off, I can spin it around. Maybe I just have to wind it back up and then it'll work again. Or it'll time travel back when it used to work. And I know you want to see me void the warranty. And with the top cover off, I see there's a plastic covering around a bunch of things. So, yeah, and if I look under the fan, there's also, wait a minute, there's another plastic cover. So, with the grill up here, I guess they'd make the, like, if any screws fell down, they wouldn't fall in the high voltage section. Hopefully in the low voltage, I mean, it could still do some damage there, but maybe not as much. The fuse is over there, but it appears to be soldered in place. Let me confirm. There it is. Yeah, the fuse is just soldered directly in. Not a big deal. There's the power switch. Oh, I took it apart while it was on. That's not very safe. So there's the transformer. It's a bit taller than I expected, but whatever. I mean, the heatsink doesn't have fins, but that one doesn't. This one does. Kind of a weird styling, but you know, the fan blowing down from the top and then out the back, and no, not really the sides. Here, I'll go ahead and unplug the fan just to get it out of the way. Well, that might come in handy in some ways. Probably not going to save anything else, if I even save the fan, but well, there's the transformer, there's a couple of transistors. I'm not going to take the time to try to reverse engineer everything in here because that wouldn't really help me much. I mean, not unless I ever got another Corsair power supply, but I mean, these things are pretty complicated, so I guess that plastic sheet right there was to make sure the heatsink doesn't touch the metal chassis of the power supply, because the heatsink will generally end up forming an electrical connection to the transistor, the bridge rectifier, whatever it is. But it almost appears on this one that the device has a heatsink on both sides for the same device. That seems a little weird. I don't think I've seen that arrangement before. I don't see the... Well, I mean, that looks big enough to be a main filter cap, but it's all the way over on the other side. What? Alright, I can see it. I'm not sure if you can see it, though. But that says 400 volts, so that's the main filter cap, the high voltage one. I told you to basically be careful about if you ever take one of these things apart. So, yeah. It's mounted, like, kind of down, like, vertically up against the board, so so there's not as much danger of touching the leads of the capacitor itself. Maybe that was the idea, but I don't think they really meant for this thing to be serviced based on, you know, the fuse being soldered in. But anyway, there goes my theory about why this plastic cover was around the fan, like, because I mean, obviously there's other things over there that'll have high voltage on them too. I mean, maybe those little jumper links on the board, and I'm wondering if those are the main bridge rectifiers that have that thing on there. So they appear to be the biggest thing. well, there's one other similarly big thing over here, so I'm not sure. Alright, so the reason the transformer isn't quite as large as you might think it would be based on the output current capability is basically because it's switched by a transistor somewhere around there at a higher frequency than the AC wall outlet power coming in, which would be 60 hertz. So like a 3 amp transformer for 12 volts would probably be the size of this whole box. Well, maybe not that big, but it'd be pretty close. So the reason a switch mode power supply has a smaller transformer for the same amount of current capacity is because by using a higher frequency, you can use smaller inductors and smaller transformers, and they'll filter just as well at those higher frequencies, even though there's less inductance or less magnetic impedance in the transformer, for example. Well, I don't see any bulging capacitors. There's a few up there. I can't really see their tops, but I don't see anything that's obviously like any obvious signs of chemical leakage from the capacitors. So I wasn't able to demonstrate the discharging technique on that capacitor, but I did basically just probe around multiple ways, keeping my fingers behind these little shields, sometimes much further back, in fact, but as long as you're behind these, you're not going to get shocked. But anyway, I was probing around looking for any kind of voltage, basically between points over in the general vicinity of the capacitor, because something over there is going to be connected to it on one end or the other, and I saw no voltage between like really any points that could conceivably be connected to that. So I'm pretty confident that I'd be safe at this point. If I were gonna try to take the board out, I wouldn't lift it from over there with my hand. I'd lift it from somewhere else. So that's the only time you'd really be exposing yourself to much risk, though. However, that appears to be the only way to probe much of anything on this board. So everything's like too tall, and you can't really get to a lot of things very easily without removing the board. So not the most accessible thing in the world, but not the most expensive power supply in the world either. So they compacted it down to fit in this ATX form factor. So I mean, a power supply this size costs about $80. I mean, what do you expect? Making it more serviceable doesn't make it last any longer. So I mean, it's more important that it lasts long and like, you know, also if it like dies, it's important for it to like not damage other components at the same time. Well, assuming it hasn't been tampered with. That's one reason I don't want to try to fix this. It's just because, like, you know, I don't want to risk losing like any data or like zapping the motherboard if I miss something in here. So anyway, this is a higher current supply. We've got pretty big inductors. Oh, I almost missed that. There's another little transformer kind of over on the other end of the board. So I'm guessing that would be for the standby supply. That wouldn't be a feedback transformer. That's what opto isolators are for. So anyway, there's all this Celastic bonding everything together so that when it's getting shipped, things don't bounce around and the solder joints don't break. So anyway. Alright, so I've measured all around and found no voltage anywhere on anything that's accessible to me right now without removing the board. So anyway, I'm not in any danger of getting a shock. There's no voltage anywhere, so it probably just discharges after a while from parasitic current draw from parts of the circuit. So I'll basically demonstrate on something else. So those two solder joints, let's ignore what's on the other side of the board and just focus on that. Just pretend there's a capacitor there and it's like a high voltage one, and I want to make sure it's discharged before I do any work. Now, you might think, well, just short it out with a screwdriver and you'll be fine. That's not harmful for me if I'm holding the insulated part of the handle. That's the important thing, to be holding the insulated part. Now, that's not going to harm me. However, it's likely to be harmful to the capacitor because you're shorting it out. But if you take some high wattage resistors, bend the leads so that they'll touch the capacitor leads, then we can bring it in there and just kind of touch them against there and do it there for a few seconds. And then after that, you can measure it with a multimeter to make sure it's discharged, or check again with a good old screwdriver or something. You might, in that case, you would probably know maybe your resistor's opened up or something, which may mean you use too low a value for the size of capacitor. So anyway, those are two 100 ohm resistors, so that'd probably be a big current dump off of charged main filter cap, but they're pretty big resistors. So, and I'm still not shorting out the capacitor, so that's still better for it than dead shorting the cap. So anyway, little safety tip for everybody. So one thing about these switch mode power supplies is that although you can turn them on without having a load on them, they usually won't regulate without a load, and generally what'll happen in that case is that there'll be a bunch of ripple on the line, and if it ripples into over voltage, it'll just shut down. But then it'll see your power supply on still grounded, and then try to turn on again. So what'll happen is that it'll just constantly cycle on and off because it keeps trying to start up, but then it's not able to regulate, so it shuts down to prevent over voltage. So you've got, like, you might hear a tick 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 noise either from a relay, if there is one in the power supply. I don't see one in here, or it might be the inductors might make that sort of sound both during startup and during fault conditions. Like you might hear a whine or a whistly kind of noise if it's being overloaded, or like a tick 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 if it keeps trying to start up but then something's detecting an out of regulation condition or an overload or something and it shuts down. So anyway, now I'm gonna do a basic sketch up of how a switch mode power supply works. This isn't really based on a particular model or anything, and this may in fact use a completely different topology for all I know. I really didn't go that far into it. I see some optocouplers right over there. There's some big fat transistors over here. A few chips on that board over there. Alright, so at the input we've got the main filter capacitor after the bridge rectifier. That's the one I was warning you about. So anyway, we've got the transformer over here and the transistor, the main switching transistor, and that'll switch on in pulse width modulation, so the more voltage it needs transferred over to the main output, the bigger the pulse width. And so the controller is going to use the feedback for the main output. This is how any power supply regulation system works, really. But it's going to compare the two, and when it sees too much of a difference, it sees it's going too low, it's going to increase the pulse width over here. And the way it controls the main transistor varies, but it'll always be isolated between primary and secondary. One common method would be to use an optocoupler or an opto-isolator. This will be a photodiode across from an LED inside the package, but they're not electrically connected to one another. It just passes a signal along, and then that signal will cause the transistor to turn on for the pulse width and then turn back off. That pulse width creates an AC waveform over here. It'll generally end up looking more like a square wave or something like that as it comes out, but that's not really a problem for the most part. It'll be turned back into DC again by this bridge rectifier over here with these capacitors, and there will be a standby supply of some form that's always on unless the main switch is turned off, which would basically just be another switch before or after the fuse. Doesn't really matter if it's in the line or somewhere. Anyway, when the power supply isn't on yet, it'll be powered from the voltage standby until you give it a startup signal, which I didn't show here. So, but if it had one, then there would be a startup signal that would make it turn on, and then another signal that would make it turn off, controlled by the user or by the computer. So the Vout would come from the main output, and VSB is voltage standby from the standby supply. And anyway, right after feedback, we've got a pretty common arrangement for a power supply filter. You've got a C, an L, an inductor, and a C, a CLC filter. It's also called a pi filter because it looks like the pi symbol. So anyway, after that, finally we've got Vout. This is more energy efficient at higher currents, and it also saves space because you can use a smaller transformer at higher frequencies and a smaller inductor, and the capacitors can also be smaller too. So switch mode power supplies are somewhat complex to design and or try to repair. And also, if there's a failure in the feedback or voltage reference or the controller, it may also cause other parts to fail even though they weren't bad. Like the switch mode transistor might fail because the controller failed. But as long as your supply has over voltage protection, it won't fry anything that's connected to the output. The other issue is also while you're repairing it, one mistake like shorting something out can also cause multiple failures, what I would call a domino failure. But with over voltage protection, the equipment being powered is still safe. I mean, under reasonable conditions, so not really counting like a lightning strike on the line. I mean, something's gonna give out if that happens. But I mean, if you got mobs like downstream of the fuse or over here, you might only lose the like a few components in the power supply if you're lucky, but I mean, there's really no safe way to simulate that kind of insane over voltage. So it's just a matter of blind luck whether whether the equipment connected to the output of the power supply survives a lightning strike. I mean, I'd be thanking my lucky stars if I was even able to recover any data, much less use the computer after something like that. So although switch mode power supplies may be more complex to design and maybe harder to repair, with proper design, a switch mode power supply could last just as long as a linear power supply and be quite energy efficient. So they both have their advantages and disadvantages. For something that draws fairly little current and price is a big deal, so like a small kitchen radio or a clock radio that plugs into the wall, a linear power supply is probably a better choice, because a small transformer that size isn't going to cost very much. So for applications where you have an AC adapter and lightweight would be a big advantage, you might even find switch mode power adapters. Now, I haven't actually taken this one apart, but I'm fairly certain it's switch mode because it's like 1.5 amps and it's pretty lightweight. I mean, 1.5 amp transformer based, like a linear power brick would feel a lot more like a brick and kind of probably be a bit fatter too, like a bit thicker. So anyway, that was just a quick look at an old power supply and just a brief summary of how a switch mode power supply works. Thanks for watching. Bye.